Now that we talked about reentrant lock, let's talk about something that's used in conjunction with reentrant lock, and that's the Java condition object. And we'll talk first about what condition variables are, because condition objects are a Java way of doing so-called condition variables, which we'll discuss have been around for a long time. And we'll talk about the pattern that condition variables implement. So one of the things to remember about what we're about to talk about is that this particular construct is a little tricky. Condition variables are tricky. So I recommend, listening carefully to the discussions, and you might want to go back and rewatch the video and maybe follow up with some of the links, because it takes a little while to get your head around what's going on here. And the reason why it takes a while to get your head around it is because there's a bunch of different moving parts. So let's first start by talking about a condition variable. I'm going to call it a CV to avoid making the slides more verbose than they need to be. So a condition variable is a form of synchronizer that allows a thread to potentially repeatedly suspend its execution until a condition becomes true. So until the condition becomes true, or you have to be a little careful here, because usually you loop while some expression is true, but what you're really trying to do is have a condition become true. Like you don't want the queue to be empty or something like that. So it'll keep doing it over and over and over again. So the thread whose execution is suspended on a condition variable is said to be blocked on the condition variable. So it's going to stay there until somebody else comes along and changes the state of the program such that the condition it's waiting on might now be satisfied. All right, so at this point, you probably have absolutely no idea what this is about, and you wonder why I keep showing pictures of Arnold Schwarzenegger, but that's a whole other story altogether. So let's give a little bit more explanation of this. So a condition variable is implemented under the hood as a queue of threads that are waiting for certain conditions to become true. And I should probably say become satisfied rather than true, because that's a little confusing. As you can see here, you're basically going to keep doing something while some condition is not satisfied. So you'll have a bunch of threads that are going to be able to wait on the condition variable until the condition that they're waiting on is satisfied. So let's replace true with satisfied. It's a better term. This queue of threads, the threads that are sitting around waiting, is given a name. And the reason I tell you this is because if you read the Java documentation, you'll see this term all over the place. It's called the wait set. So just think about it as a queue or a set of threads that are waiting for their chance to check if the condition is now satisfied or not. And it may or may not be in FIFO order. We'll talk about that later. Condition variables are used when mutual exclusion, which is what we get from reentrant locks, alone is inadequate. You guys probably don't remember who this guy is, except for the fact he was a disgraced politician from a couple years ago. But long before he was a disgraced politician, he was actually a comedian on Saturday Night Live, and he went by the name of Stuart Smalley. And he would always say he was a self-help coach who would always feel inadequate. And he would say, I'm a loser, I'm a failure, and so on. It was actually pretty funny. So when mutual exclusion alone is inadequate, like poor Stuart Smalley, condition variables can help to make them better. Why would mutual exclusion alone be inadequate? Well, one reason is because you may end up having your threads busy waiting and spinning. They're spinning, spinning, spinning if you don't use condition variables. So if you want to check something, like if you want to wait until the queue is not empty and you don't use a condition variable, and you only use a mutex, you'll have to sit there and spin and check and check and check. And that's wildly, wildly inefficient. Okay, so that's one reason, inefficient use of resources. Another is a mutex alone is not capable of providing coordination. So coordination, of course, is how threads tell each other to take turns doing something. You go first. No, you go next. No, you go next. No, you go next. Think of it like the ping pong example we talked about. And basically what that means is when a thread encounters some internal state that prevents it from making progress, it probably wants to let someone else go. So for example, if you're trying to dequeue something from a bounded queue and the queue is empty, then you're going to want to wait for the queue to be not empty, and you darn well better let somebody else go who might put something in the queue so that the queue will be not empty. So you can go ahead and do your thing, right? So that's about coordination, taking turns doing something. So a good example is waiting on an empty list. That's an example of something where you might have a thread that can't make forward progress until the list is no longer empty. All right, so that's kind of the background of this. Now let's talk about something called guarded suspension. And we typically use we typically use condition variables whenever we need to implement the guarded suspension pattern. And you can read about this pattern here. And basically what the pattern says in a nutshell is if you can't make forward progress, put yourself to sleep and wait until you can make forward progress. So we apply this pattern on operations that can only run when certain things become true. So we want to do some processing, but we can only do it once some condition is satisfied. So here are some things that need to be satisfied. We need to acquire a lock, so we have mutual exclusion. And we need to make sure that the precondition has become true. So what we're going to do here is we're going to keep looping as long as our precondition is not true. And every time we loop, if the precondition is not true, we go to sleep. And that's the condition. That's how the condition object works. So what is going on here is thread T1, which is the one that's trying to do some processing. When it is not able to make progress because the condition is not satisfied, it's going to go ahead and suspend its execution by calling await. And it's going to continue to wait until the condition may be satisfied. And the key thing here is may be satisfied. And I'll explain in a second why it's so tentative, why it's just may and not is satisfied. And that is, in some sense, why there's a loop here. So we acquire the lock, we check the condition in a loop with the lock held. That's important. If the lock needs to be held, check the condition because we may be accessing shared state, and that state could be changing out from underneath us if the lock isn't held properly. And then, if the condition is not satisfied, the thread calls await. And await does two things atomically. It will release the lock and go to sleep. So those two things must happen at the same time. At some point, after the world has changed and we've been signaled, and we'll talk about signaling later, this await call wakes up, the condition has become satisfied, and then, and only then, can we make it through the guard, and then we can do the operation processing with the lock held. So the lock is still held, we're doing the processing, the condition is satisfied at that point, and we're able to do our thing. So this stuff here, grabbing the lock and then waiting in a loop while the condition is not satisfied, that's the guarded suspension pattern. And then once we have that condition satisfied, then we can do our thing, we can do our work. Oops. So the key thing to note here is that we're not going to get out of this loop here until someone comes along and signals, some other thread signals this condition that will cause it to wake up, recheck, it'll cause it to wake up, reacquire the lock, and then check the condition with the lock held to see if it's satisfied. If it's satisfied, we do the operation processing. If it's not satisfied, we go back to waiting again. Notice how the lock is always reacquired before we recheck the condition. So again, we're in a loop. Await does two things. It will wait, it'll release the lock and wait, and then when someone signals it, it'll reacquire the lock, and then the control flow will go back to the loop. These conditions here can be arbitrarily complex. I show it like it's a method call, but it could actually be anything involving shared state, some expression, some Boolean variables, whatever you want it to do, while the count is less than 0 or less than equal to 0, whatever it needs to be. So it's something that typically involves shared state. The key point here is that this check, the condition, always occurs with the lock held. Waiting on a condition variable, when you do a wait, that atomically releases the lock and suspends the thread. So it's like our typical atomicity thing. You don't get to do anything until you go to sleep and the lock is unlocked at the same time. And this thread that's waiting, in this case, this guy, gets suspended until some other thread signals the condition variable. When the thread signals, it wakes up and it has to reacquire the lock. So it go from unlock back to lock. Once it's locked, it rechecks the condition to see if the condition has been satisfied. Now, here's the part that's interesting. That's why I used the word may. It's not always the case that just because somebody woke you up, you can get the resource you're waiting for. How could that be, you might ask? Well, one thing that might happen, let's say for sake of argument, we've got multiple threads that are all waiting for the queue to be not empty. That's a perfectly valid situation. In fact, that's how a thread pool works. You have a pool of threads like our fixed size thread pool for the executor framework or executor service. And all of those threads are going to be sitting there waiting for the queue of work, the queue of runnables, the queue of callables, whatever, to be non-empty. So there could be, n, let's say there's 4 threads waiting. And when there's something in the queue, right, when someone puts something in the queue, when someone submits a job or executes a task, or submits a task, at that point, now there's something in the queue. So the way this is going to work is, maybe we're going to wake everybody up, because we don't know which one is going to make it there first. So we wake everybody up, and they all come along and try to grab that item out of the queue. Think of it like, if you're at a pet store and you're going to feed the puppies, you might have a bowl of food, and you let all the puppies run over to grab the food or grab the ball or grab the chew toy or whatever. And whichever one gets there first gets it, and the others have to wait their turn. So just because someone has, let the puppies out, just because somebody has said, hey, threads, you can go, doesn't mean that by the time they acquire the lock and get exclusive access to the shared resource, someone else hasn't snuck in at the last nanosecond and grabbed it there first. So because of that, we always have to, or almost always have to recheck the condition with the lock held. And if we are still not able to get it, we have to go back to sleep again, right? So it's just like the puppies. If one puppy doesn't get the chew toy, it'll have to go back to sleep. Yes?
Now signal, can you give it
Great question. No, signal by itself doesn't do that. But there's a really cool pattern called the specific notification pattern, which basically works the same way by having each waiting thread have its own condition object instead of having one condition object that's shared by all the threads. And that does more or less what you just said. So if your goal is to wake up the next waiter in line, and each waiting thread has its own condition object, then you can signal that particular condition object, and that'll let that particular thread wake up. And you'll actually get a chance to implement that. Yeah? Yeah, great question. That's a good point. So if you don't care about fairness, if it's just like, wake somebody up, whoever gets it first, you're not trying to keep the puppies, you're not trying to feed the puppies fairly. You're just like, whoever's most aggressive gets the chew toy or whatever. Then you just throw it out there, and it's like feeding alligators, right? You throw the food out, and they all run and attack each other, and whoever's the strongest gets it. If you're into fairness, then the kind of thing you're talking about would make a lot more sense. So yes, that could be used. In fact, that's what specific notification is all about, is being fair. It's making sure the specific one runs, whatever specific means. It could be the one that's next in line. It could be the one that's highest priority. Whatever it is, whatever fair means, or whatever specific means, you can have each one have its own condition object. Yeah, those are great questions. So the long and the short of it is, the operations run with the lock held after the condition is satisfied. Okay, so that's the end of the overview of ConditionObject. I think you will hopefully appreciate from the discussion we had, it's a bit subtle. And so you have to get used to certain idioms, which we, of course, will talk about, and you'll get a chance to play around with them.